Hello. Let's talk about today sequences. So a sequence of numbers is just what the name suggests, it's a sequence. So it's going to be a function where we are gonna tell this is the first element of the sequence, that's the second element of the sequence, that's the third, and all the elements of the sequence are going to be real numbers. So from the mathematical formal viewpoint, a sequence xn, when n goes from 1 to infinity, is just a function, x, which domain n star is the set of positive integers, to the set of real numbers. And it's just that we change a little bit the usual notation. So the usual notation for a function should be x evaluated at n. And instead of using this notation, when we talk about sequences, we use this notation. So the n becomes an index, okay? So instead of writing something like x7, instead we write x7 like this, okay? Instead of using the functional notation, we use the notation that is typical of sequences. All right, examples. The most boring sequence in the world is the sequence such that its first element is k, where k is a real number. You fix any real number, k, that you like, and the second element of the sequence is k, the third is k, the fourth is k, k forever. He always repeats the same value, okay? This is a symbol for every positive integer number. You always apply the formula, x is always equal to k, xn is always equal to k, okay? So it's the most boring sequence in the world. The second one is this xn equals n. So here x1 is 1, x2 is 2, x3 is 3, and so on and so forth. Okay. Third example, Pn, instead of x I'm using p, because now this is the sequence of prime numbers. Okay, so Pn is the nth prime number. So P1 is the first prime number, which is 2, P2 is the second prime number, which is 3, P3 is the third prime number, which is 5, P4 is the next prime number, which is 7, P5 is the next prime number, 11, P6 13, P7 17, P8 19, P9 23, and so on and so forth. Okay? And you can use this to construct other sequences. So here's zeta n, zn is going to be Pn over square root of n plus 1, where this Pn is given by the prime number sequence. It's just the nth prime. So zeta 1 is the first prime number over square root of 1 plus 1, which is square root of 2. The first prime number is 2, so it's going to be 2 over square root of 2, which is square root of 2. Then zeta 2 is going to be P2 over square root of 2 plus 1, right? Using this formula here, P2 over 2 plus 1 square root. So P2 is 3, 2 plus 1 is 3, so it's 3 over square root of 3, which is going to be square root of 3. Zeta 3, what is going to be zeta 3? It's going to be the third prime number, 5, over square root of 3 plus 1. 3 plus 1 is 4, square root of 4 is 2, so it's going to be 5 over 2, and so on and so forth. And goes forever, okay? So these are infinite sequences. They go on forever and ever and ever and never stop. So we have infinite many values. So a sequence xn from 1 to infinity is bounded above or bounded below. So it's bounded above if there is a number m, a real number m, so that all members of the sequence are smaller or equal than m for all indices n in the sequence. Okay? So in this case here, the sequence is bounded above by this number m. Okay, so if a sequence is bounded above by 25, it's also bounded above by 35 or by 1,000,000, for instance. Okay, so this m is not unique, but yeah. And it's bounded below in red here if there is a real number such that the sequence never goes below this m here. Okay, the sequence is equal or above the value m, always, for all indices n. Okay? And finally, a sequence is bounded if it's bounded above and below. Okay? A sequence is bounded if there exists a number m such that in the absolute value of is smaller or equal to m. So the sequence is never smaller than negative m, and the sequence is never bigger than positive m. Okay? So 3 definitions here: definition of bounded above, definition of bounded below, a definition of bounded. Okay? And you can prove that a sequence is bounded if and only if the sequence is bounded above and the sequence is bounded below. Okay? Now, next definition, and perhaps the most important one, is this one. When the sequence will converge. So a sequence xn from n equals 1 to infinity is convergent to a real number L. So L we call the limit of the sequence, if the sequence is convergent. If for every epsilon greater than 0, there exists n0, index n0, so such that this bar here is such that for every index n greater than this n0, the distance between the sequence and the limit is smaller than epsilon. So here the xn is epsilon close to the limit, L. Okay? And this is a tail property, which means it doesn't matter what happens in the beginning of the sequence, we care only about what happens in the tail, when we go far, far away. Okay? Notation, if there is a limit, we can write the limit of xn when n goes to infinity equals to L, or we can just write this. We put xn, an arrow to L, and we write something as n goes to infinity. This is a short notation for this, and either one is a short notation for this very long, complicated sentence. Now let's try to understand a little bit this long sentence here. So suppose I want to show that L is the limit of my sequence, and I'm gonna plot the values of the sequence on the vertical, okay? The xn, so this is the xn axis, okay? I plot xn as a function of n. The horizontal here, I have the index. So x1 is this height here. The value of x1 is this. How big I have this distance here is x1. This little distance is x2, could be negative as well. This big distance here is x3. All this distance from this point to this is x3. This height here is x4. This height here is x5, and so on and so forth. Okay? So, for this sequence to be convergent, you have to satisfy this for every epsilon, no matter how small. So now someone tells me a very small number epsilon, small but positive, strictly positive epsilon. So I come here from my limit and I go epsilon units up and epsilon units down. So this red point is L plus epsilon, this red point is L minus epsilon. And I trace these auxiliary lines here in red. And I make sort of a road or a tunnel, right? So what's the definition saying is that eventually, at some point, there will be an n0. It could be very big, I don't know how big. It will depend on epsilon, okay? So that such that if I go on in that direction after this n0, so this n0 is here, after the n0, the distance between the sequence and the limit is smaller than epsilon, which means I'm going to be inside of the road. Okay? From here on, I must be always, I can go up and down, I can jump around, but I have to be inside of this tunnel. Okay? If I have a single guy outside of the tunnel, then my n0 is not good enough. We have to further investigate whether the sequence is convergent or not. Okay? So that's the definition. And if you are nasty, you can pick a really small epsilon so that it's going to be very hard to be inside this very narrow strip here. But if the sequence is convergent, eventually you will be able to find an n0 such that after n0 all the elements of the sequence will be inside of the tunnel or inside of this road. You cannot have anything below this line, you cannot have anything above this red line. Okay? So that's the definition of convergent. A few properties now. So perhaps I should write here a few properties of the limit. Number one, uniqueness. So if xn converges to L, this limit is unique. That means you cannot have a sequence converging to two different limits. If it goes, the limit of the sequence is 45, that's it. It cannot go to 47 or to 45.1. No. There's only one limit. Maybe a sequence does not have any limit whatsoever. Okay, that's possible. So in our examples here, the sequence of prime numbers is always increasing, right? And it always increases by at least 2 after the first jump from 2 to 3. Then it always goes up by 2. So if you pick an epsilon smaller than 2, there's no way you're going to be around any tunnel. So this Pn does not converge. Okay? By contrast, the constant function, the constant sequence, which is always k, always that same value, it converges. Guess to what's the limit? Is that value as well, right? It's k is the limit of the constant sequence. Okay? But if we have a limit is unique. You can only have at most one limit. Maybe there is no limit, but if there is at most one limit. Okay? The second property is that if the sequence is convergent, if xn goes to L, then xn is bounded. And in this diagram here, it's not very hard to say. So if this is a diagram representing a convergent sequence, what is the upper bound for the sequence? Well, pick here before n0, you have finitely many values of the sequence. Pick the largest one and also pick this L plus epsilon, and for sure the highest between the highest value until n0 and this L plus epsilon is the upper bound. So it's bounded from above. And also the sequence, the convergent sequence will have to be bounded from below. Well, pick the smallest between these finitely many n0 initial values of the sequence and the L minus epsilon. The smallest between these two numbers, it's a lower bound for the sequence. Okay? So if the sequence is bounded from above and from below, so it's bounded. Okay, so every convergent sequence is going to be bounded. Okay? Third one, it's an interesting one. Suppose you have three sequences, an, xn, and let's say some bn here. Okay, so we have three sequences, and suppose further that an converges to some number a, some real number a. So suppose the sequence an is convergent, and the bn sequence also converges to a. Okay? And suppose further that an, xn, and bn holds for every n greater or equal to some n0. Okay, so after finitely many terms, this xn becomes in the middle of an and bn. So think of a sandwich. This is bread, and this is the ham. It's a ham sandwich. So xn is between the two slices of bread, sort of speak. Hope you got it. In this case, what's going to happen to xn? So the lower bound is converging to a, the upper bound is converging to the same value, so the middle will have to converge to the same value as well. Then xn will also converge to a. Okay, that's the sandwich property of converging sequences. And converging sequences have the expected algebraic properties. For instance, if the limit of xn is some x star, the limit of yn is some y star, then the sequences, if you create a sequence zeta n equals xn plus yn, what's happened? This zeta n will also be convergent. It will converge to, guess who? X star plus y star. Okay? What else? Suppose that xn converges to x star, so the sequence zeta n equals lambda xn converges to lambda x star. So if you multiply all members of a sequence, of a convergent sequence by a real number, this lambda is any real number, then the limit of the new sequence is going to be the real number multiplied by the limit of the old sequence. You could rewrite, I suppose, this as something. You could write the same thing here. So the limit of xn plus yn is the limit of xn plus the limit of yn. Always when n goes to infinity, you have to write here. Okay? So this is the very basic, very fast introduction to limits of sequences. And in general, the topic sequence is very important in finance and mathematics, economics, a range of disciplines. Okay, hope you enjoyed. That's it for now. Bye bye.